Om Shri Sai Ram. Welcome to the second session of this chapter, Magnetic Effects of Electric Current. Today we are going to talk more about the current carrying conductor. What happens around current carrying conductor? Before diving into that concept, let us answer the previous questions which I have given you in the last home assignment, right? Okay. Then go and let's answer them. What is the first question I have given you? Why does a compass needle gets deflected when it is brought near bar magnet? Right? So he is asking, when you bring a bar magnet near a compass or when you bring a compass near a bar magnet, why the compass is getting deflected? Right? Now let us see the answer and I'll explain you the answer. The needle of a compass is a small magnet. So you can see in the compass you will have the north pole and south pole, right? So it is also a small magnet. That's why when a compass needle is brought near a bar magnet, its magnetic field lines interact with that of the bar magnet. Hence a bar magnet needle gets deflected. What it tells is, magnetic needle in the compass also has a magnetic field lines, right? Because it is a magnet. Every magnet has a magnetic field lines, and bar magnet also has its own magnetic field lines. When this compass comes under the influence of the bar magnet, it gets caught up in that magnetic field lines, hence it gets deflected. It is like a flag in a wind, moving wind. Flag gets deflected, right? In the same way, magnetic needle of the compass gets deflected in the magnetic field lines of the bar magnet. So why it happens, in what direction it goes, why it goes in that direction, in the direction of the north pole, we'll discuss later in this chapter. Alright. Now, what is the second question? The answer is being displayed here. The second question is, I asked, when you have a magnetic compass, right, and also you have a bar magnet on a piece of paper, but you observe that that the compass is not getting deflected, right? You have a magnet and you also have a compass, but those two are significantly distant away from each other, and we are claiming that bar magnet, the compass is not getting deflected. Why is that? We know the magnetic field lines around the magnet originate from north pole and comes to south pole, right? So if anything is kept in between the field lines, it will experience a force and gets deflected, and the magnetic compass gets deflected. When it cannot deflect, when the magnetic field lines which is originating from north pole and coming to south pole, in between, if you don't have that, if magnetic compass does not feel that influence of this magnet, how can it deflect? It won't experience any force, right? So even though you have a bar magnet and a compass nearby, but this bar magnet has no influence, is not influencing this compass. This compass has no influence of this bar magnet. No field lines are going through this compass. Then there is no way, because you can't expect a deflection there, because it is not in the magnetic field of bar magnet, right? So this answers your second question. Now the third question is very interesting question, and we emphasized about this in the last session also. Can two magnetic field lines intersect? Yes or no? And you need to justify your answer. Okay, before seeing the answer, let us suppose explain what the magnetic field line is and then arrive to our conclusion. Okay, let us draw for you. Now let us suppose you have a bar magnet. This is bar magnet, north pole and south pole. As we did an experiment with our magnetic compass, what we saw, the magnetic field lines originate from north pole and go into south pole, right? This is the direction of magnetic field lines. So you have many more field lines around it. Okay. So what is the definition of the magnetic field line? So how did we do the experiment? We placed the compass near the bar magnet and dragged it around and marked all the points where the compass is pointing north pole and joined all that points, right? So what is the conclusion we got? That this field line means the force experienced by the north pole of the compass in this field, right? The north pole of the magnetic compass is experiencing the force. It is in this direction. So if you put a compass here, it will have a north pole in this direction. That's why you joined all these similar points so that we got a magnetic field line. Okay. Now we are asking the question, can two magnetic field lines intersect? For example, let us suppose two magnetic field lines intersect. This is one line, okay, this is one line and this is another line. Two magnetic field lines are intersecting. So what does the direction of the magnetic field line tell you? Direction of the magnetic field line tell you the direction of the north pole of the magnetic compass, right? If you put a compass here, its north pole direction is in this way. If you put a magnetic compass here, its north pole will show you the direction in this way. So here, when you have the magnetic field lines intersection, there should be a common point, right? This is the common point. Now, if I put a magnetic compass here, where does the magnetic field line, where does the magnetic needle deflect? It should always deflect towards the north pole. Now, this field line is telling this is the north pole. This field line is telling this is the north pole. So this compass will get confused. Is it practical? Always we see compass will direct towards the north pole without any confusion. It knows where the north pole is. So our definition of the field line allowed us to wash out this possibility, because no field line can intersect. Magnetic compass knows where the north pole is. When the compass is only directing towards the one point, there is no question of two field lines intersecting with each other. Okay, so no field line will intersect with each other, no field line will interfere with each other. They will start from north and go to south without disturbing any other field line. Alright, so this is what we have answered here. No two magnetic field lines of force never intersect. If two magnetic field lines of force intersect each other, then at the point of intersection there will be two different directions of magnetic field lines, which is not possible. It is not possible to have two magnetic field lines at the same point. You saw in the intersection point, if you put a magnetic compass, it shows you two different field lines. One is telling this side is the north pole, one is telling this side is the north pole. That is not possible. So we don't have any intersection of magnetic field line. So these fundamentals you need to get rooted in your mind so that you can grasp the concepts very easily further. Okay, so let us go to our topic today. This answers the last session questions. Today's topic is very interesting. As we saw in the oysters experiment, that current carrying conductor is just behaving like a magnet, right? Now we need to know the properties of that magnetic field and what can we make use of that, right? It is a phenomenal invention, not discovery. It is a phenomenal discovery. So let us go and explore further about it. So now we know the direction of the magnetic field for a bar magnet. The direction of the magnetic field lines in a bar magnet, it starts from north and goes to south. This is fixed. So let us study about the direction of the magnetic field when you have a current carrying conductor. In which direction it goes? Let us see. Okay. Here the setup is, you have a flat plane, this is the conductor, no current is passing. Okay. Now the current is passing, see the deflection of the magnetic field, how it is going? It is outgoing current going up. So the north pole is deflected towards the anti-clockwise. Now current is changed, it is going inside. Now the north pole is deflected in the clockwise direction. Right? Now there is no current, no deflection. When you on the current, you will have a magnetic field and that changes the needle. See, now let's on the current now. On. Just deflected. The current is going up. Now you can see the what? Deflection is anti-clockwise. The north pole is in the anti-clockwise direction. Incoming current, again the current magnetic field line changed. Then now the north pole is behaving differently. Let us see in the pictorially. This is how it is behaving. Here it is incoming current, it is outgoing current. You just can simulate this is outgoing current. The magnetic field lines are this way. This arrow shows you the direction of the north pole. See, the north pole is directing in the anti-clockwise direction. Now it will incoming current, this diagram. It is going in the clockwise direction, the north pole. You can see it. No current, when you have no current, you cannot produce a magnetic field, so it gets undeflected. So what's your conclusion by seeing this? That means if I change the direction of the current, the magnetic field lines also changes. The direction of the magnetic field lines also changing, right? You can see here, when the current is going down into the cardboard, the magnetic field lines are in clockwise direction. Now when you reverse the current, the magnetic field lines are in anti-clockwise direction. You can just cross-verify using this experiment. So let us boil down to one conclusion. Change in current direction also changes the magnetic field direction. So seeing this experiment, we can conclude that change in the current direction, when I am changing the current direction, one time it is going into the board, one time is going outside of the board. That means I am basically changing the direction of the current, which also changes the magnetic field line, direction of the magnetic field lines. Now in the experiment also, we have observed that when you increase the current, when you increase the flow of current, that means basically what I am increasing? I am increasing the charge flow. That is what I am increasing. The current flow means the rate of charge, the rate of movement of charge. That is called electric current. So I am increasing the charge flow per unit time. So when I am increasing the charge, what? I am increasing the magnetic field around it. If some quantity of charge is producing some magnetic field, when the large quantity of charge is moving, by intuition it should create more magnetic field, right? Comparatively before. That is what we observe here. When we take a compass and place it here and increase the current, it will feel the north pole of the compass will feel a greater force when you have more current. That means you are having more magnetic field around it. When you lessen it, the magnitude of the magnetic field will be lesser and lesser. Less current, less magnetic field. So when you have a less magnetic field, the force on this north pole of the compass will comparatively become less. What is the magnitude? What do you mean by the magnitude of the magnetic field? When you have more magnetic field lines, right? So pictorially, let me show you. So let us suppose I increase the current here. So what happens all of a sudden? The magnetic field lines will increase like this. Okay. Suddenly the magnetic field lines increase, so that the force experienced by a compass or any magnetic object will experience more force. It will experience more force. Now if you decrease the current, what happens? When you decrease the current, the concentric field lines will be like this. If you take a area here, how many field lines are passing through this area? Only one field line, right? For suppose here similarly I increase the current. Now the same area you take here. The same area you take here. How many field lines are passing through this? This is one field line. This is one field line. That means the magnitude of the magnetic field is more here, less here. Right? The intensity is more here, intensity is less here. Because I increased the current here relative to this. So when I am increasing the current, I am also increasing the magnitude of the magnetic field, which means the intensity of the magnetic field here. I hope it is clear, right? So now we can arrive to a conclusion that magnitude of the magnetic field at the given point increases as the current through the wire increases, right? We saw two similar points, how they behave differently when you increase the flow of current, right? I hope this is clear. Now we are saying that change in direction of current also changes the magnetic field line. But we need to have a correlation between the current direction and the magnetic field direction. We can't say qualitatively that I am changing the magnetic field current direction so that the magnetic field direction is changing. See, here the current is going down, that's why the magnetic field lines are in clockwise direction. Here the current is going up, that's why the magnetic field are in anti-clockwise directions. So we need to relate these two, forming a rule. If we fix it, what happens? Okay, flow of current if the flow of the current is in this direction, the magnetic field direction should be clockwise. If the flow is in this flow of current is in this direction, upward direction, then the magnetic field line should be in the anti-clockwise direction. That kind of a rule we need to bring in, right? So we need to go and form a rule for that, which we call as right hand thumb rule. Okay, what the right hand thumb rule says? Assume that you are holding a current carrying conductor. Okay, I am holding a current carrying conductor in your right hand, and the thumb should point towards the direction of the current. Let us suppose the current is going from here to up. That means it is going upwards. My thumb should point upwards. Okay. Then your fingers will wrap around the conductor in the direction of the magnetic field lines. Okay. What it says is, if I am holding the current carrying conductor in my right hand, and I should point my thumb towards the direction of the current, okay, then the rest of the palm, the rest of the fingers will wrap around. The direction of this wrapping will give me the direction of the magnetic field lines. Understood? If the current is going up, the direction of the magnetic field lines will be in this direction. It will be in the concentric circles, as you saw. It will be in the concentric circles, right? The center will be same with different radius. So the magnetic field lines will be in the in this direction, in the direction that your rest of the fingers wrap. If the current is going towards you, see, the thumb is in your direction and the rest of the fingers is in this direction. That means you are having an anti-clockwise direction of magnetic field. Okay. If the current is going inside the board, the thumb is towards the direction of the current and wrap around the fingers, and the direction of the wrapping gives you the magnetic field. That means it is now in the clockwise direction. Here it is in the anti-clockwise direction. I am changing the current, I am also changing the magnetic field direction. Here it is in the anti-clockwise direction. When you point inside, it is now in the clockwise direction. So this will explain our last experiment, right? When I am changing the current, the magnetic field lines is changing. So the same thing I am doing here, right? So this tells you the direction of the magnetic field line. Now let us see pictorially. This is the rod, the thumb. He is pointing the thumb towards the direction of the current. Current will always go from positive to negative terminal. So the wrapping of the fingers direction will give you the direction of the magnetic field. What is the direction of the magnetic field? Direction of the magnetic field is the direction of force experienced by the north pole of the magnet, right? Okay, and this rule also called as Maxwell's corkscrew rule. What is Maxwell corkscrew rule means? Corkscrew rule means, let us assume this as the screw, right? And this screw will assume as a conductor, a wire. Now we just rotate this using thumb. So what this rule, Maxwell's corkscrew rule, tells us is, when I rotate the thumb, this rotation of thumbs gives me the direction of the magnetic field. Alright, and the direction of current will be given how the screw advances. Screw advance direction will be the direction of the current. See, if I am rotating the screw in the clockwise direction, if my thumb is rotating in the clockwise direction, so the screw will go inside, right? Screw will advance inside. That means current direction is into the board, and the and the magnetic field direction is in the clockwise direction. This is the same thing that our right hand thumb rule says, right? Your thumb pointing towards inside the board and wrap your fingers, it is in the clockwise direction. So the both rules are similar, and so right hand thumb rule and Maxwell cork rules, we can use anything to our intuition. Okay, now you have seen the magnetic field lines, how the magnetic field lines of a straight current carrying conductor. This is straight, how the magnetic field lines are in circular, right? You have a center here. These are all concentric circles with different radius. Right? This is the first circle radius, this is the second circle radius, this is the third circle radius. Now let us study about the magnetic field line of different curvature. What is that? Let us see. Current in a circular loop. This is very interesting. Okay, until now we have only studied about the current carrying conductor in a straight line. Let us see how the current carrying conductor in a circular loop produces the magnetic field. Okay, let us see. Let us have an experiment. See, this is the cardboard. For example, this is the cardboard. You have a the setup is, you have a copper coil like this going through the cardboard into putting the hole inside and coming down, and you have a electric source attached to it. Okay, this is the similar thing. So half of the coil is up, half of the coil is down, and it is attached to a source, power source. Now the current is going in the copper coil. Let us study about the magnetic field. So you can see here, when you put a cardboard and you can see the magnetic field line, let us take this small element as one straight conductor, this small element. So this circular coil is addition of such small elements. Okay, so this small element will produce what? Circular magnetic field around it, right? We saw current carrying conductor, straight current carrying conductor will have a circular magnetic field lines. So this will have a circular magnetic field lines. How the current is flowing? In this fashion, right? That means here at this point the current is going up. When the current is going up, what will be the direction of the magnetic field line? In this fashion, right? So see, the current will be in this fashion. In the same way it is behaving. It is behaving as a small straight current carrying conductor. Okay, if you see, if you use your right hand thumb rule, see, let us assume coil, copper coil is coming out. What will be? It will be in the which direction? Anti-clockwise direction, because the current is going up. This is the direction of current here. Now let us take this element. This also we can assume as a small straight current carrying conductor, right? Now, but the only difference is here the current is coming down, there the current is going up, here the current direction is changed. So usually we expect the change in the magnetic field direction. Yes or no? Right? So what will be now? Now current is going in this direction into the board. So it will be in the clockwise direction. Like wrap your finger. This is the direction of the current. Wrap your finger. So this will be clockwise direction. Understood? Now the key point here is, if I place a object here, north pole of a magnet here, how it will feel the force due to this magnetic field? You can see, due to this magnetic field it will feel a force upwards, right? Now due to this magnetic field, how it will feel? Also upwards. See, inside the coil those two directions are uniform. Because of this magnetic field, the magnetic field line inside this coil is uniform. It is going in the same direction, upwards. Because of this also, because of this magnetic field also, the force exerted on this element is in the same direction. It is adding up. It is adding up. Do you see this wonderful phenomena? Here you have an upgoing current, here you have a downgoing current. When you see the field lines inside this coil, those two are adding up in the same direction. It is also having in the same direction, it is also having in the same direction. Likewise, if you see in every element on this, we only took two elements of this coil. If you see every element on this coil, how it turns out to be is like this. So every element will have a magnetic field inside. Every element will have a concentric magnetic, because every small point we can assume it as straight current carrying conductor. It will have a circular magnetic field. So whole the circle you will have a concentric circles of magnetic fields. So inside the coil you can observe every element's magnetic field is in the same direction. See, is in the same direction. Is a uniform direction. Can you simulate this to anything you have studied up to now? Just take a compass here. Take a compass here. How the north pole will deflect here? The direction is upwards. So north pole will deflect up. Okay. Now how will the compass deflect down? Again the magnetic field direction is upwards, so the north pole will be upwards. That means you have to see here this compass is deflecting away from this circular coil. Here it is towards the circular coil, right? So current carrying circular coil we call as any current carrying conductor we call as a small magnet. How this is behaving you can see here. Upwards, what kind of a pole we can assume here? The north pole is pointing away from it. That means we can assume here upside the north pole, right? Because the compass is pointing away from the circular coil. At the bottom, the north pole is towards the circular coil. Here I can say this is south pole, right? This is north pole, I can intuitively say, right? Because the compass is showing the direction away from the north pole. Here the compass is showing the direction towards the south pole. Like poles repel, unlike poles attract. So this is behaving as a small bar magnet, but of a very, 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 very thin length, right? If I draw a bar magnet here, this will be the field lines, right? This will be the field lines. Inside the magnet, it will be from south to north, right? But what is the difference here? The difference is it is very, 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 very minute thickness it has. Here north and south pole, between north and south pole you have so much thickness, but here you have very less thick if you compare it to bar magnet, right? If I want to have the magnet, full magnet, if I want to increase the thickness of it, what I will do? What should I do? Let us see. Let us add more coils. If you add more coils, what happens? I am adding more coils here, right? See, one coil we have studied, every element of this coil will produce a magnetic field inside the coil in the same direction, right? In the same direction. Now, to increase the length of the magnet, every coil is, when we studied about the individual coil, we thought this as a very small magnet of very small length. I want to increase the length of the magnet. I added up more coils. The current direction is similar. Every coil is similar to each other with having the same radius. So what happens? They will exert a similar magnetic field inside the what? Inside the coil, even outside the coil. So what happens when the directions are same? This coil also exerts the same direction of magnetic field line. So what happens when you attach these many coils? The magnetic field will add up. All the coils' magnetic field will be add up, and you see a uniform magnetic field inside the solenoid. Now you see, you take a bar magnet here, north pole, south pole. Is it not similar now? The field lines going from north pole and coming towards the south pole. Here also the same thing. The bar magnet also we studied the same thing. The field lines come from the north pole and going inside the south pole. How wonderful it is. So there are many advantages of this. What are the advantages we study in the further? But for now, we are satisfied using this experiment. And this equipment we call as solenoid. This helical coil, the so many coils which we attached, This whole setup we call as solenoid. And how the field lines inside the solenoid is, inside the coils of solenoid is, they are uniform and they are parallel to each other, because every coil contribute the same magnetic field in the same direction. They will all merge and they will add up and form a parallel lines. Everywhere the magnetic field intensity will be same. If you take a small area here, small area here also, small area here also, in every area, in every cross section of area, you can see same number of magnetic field lines will pass. Here if you take the area, if two magnetic field lines pass here, similar areas take here, here, anywhere, only two magnetic field lines will pass. This is for example I am saying. So what we conclude? Field lines inside the solenoid are parallel and uniform at all points. They are uniform at all points. Right? Now let us go and explore whether it is really a magnet or not, and let us see about the advantages of it. See, solenoid, no current. Now I put a current, the magnetic compass is deflected. Only observe about the north pole, which is red in color. Again, let us go. No current, no deflection. Okay. Now we drag again. North pole is attracted. That means this is south pole. Unlike poles attract, this is going away. This is north pole. The current changed. Now here it is acting north pole. Now north pole is being attracted. This is south pole. How wonderful it is, right? If you have a magnet, bar magnet, if you have to change the north and south pole, you have to rotate the magnet for the bar magnet. Here, I do not have to rotate the bar magnet. I just change the current, it changes the pole on the left and right side. Right? And one more advantage is when I want it as a magnet, I switch on the current. When I switch it off, it is just a conductor. It is just a wire. When I want the magnet, at that time only I switch on. All the time I don't want this as a magnet. So this is how wonderful an instrument is this, right? Yes, this kind of a magnet which is produced from passing electricity, that kind of a magnet we call as electromagnet. Usually we put a small soft iron core in between the coils so that it gets magnetized even more, and we call that too as a electromagnet. Yes, this is an electromagnet. Now let us see what are the uses of electromagnet. You can see this. This is a huge electromagnet. Why we are using here? Electromagnets are used to sort out scrap metal. You have a dump, you have a mixture, you have a metal in that. How do you identify that? You take a large electromagnet and switch it on. All the magnetic particles will attract, the rest will be down. This is how easy the process is. Then the large cranes we use to transfer the large bulk of iron or any heavy metal object. What we use? The cranes will use electromagnet to lift it and displace it. So this is how the electromagnets are useful. Now let us go and explore about the force on current carrying conductor. So from the starting of this session, I was saying about the force experienced by this compass, force experienced by the north pole of the compass. So I use frequently the term force, right? Now let us go and explore how the force on the current carrying conductor, the direction of the force of current carrying conductor due to the external magnetic field. Okay, let us go and explore that. Force on the current. When you listen to the term called force, the first thing comes into your mind are Newton's laws, right? So everybody is familiar with the Newton's third law, right? What is the Newton's third law? Action is equal to minus reaction. That means every action has an equal and opposite reaction. If two bodies are here, how much force it is exerting on this body is the same force that is being experienced by this body due to the body 2. If this is body 1 and this is body 2, if this is action, if the force on body 2 is action, the force on body 1 is reaction. Understood? And the only difference is it will be in the opposite direction. If you have a body A and body B, force on body B due to body A, for suppose it is in this direction with some magnitude, okay, for suppose say 4 newtons. Now the force on body A due to body B will be exactly same in the opposite direction. If this is 4 newtons in this direction, for suppose let us say it is positive x-axis, it will be negative x-axis, it will be minus 4 newton. So it will be same magnitude, 4, same magnitude, but the direction is different. It is minus, it is in the opposite direction. Okay, let us use this concept to derive or to identify, to observe the force of current carrying conductor, experienced by current carrying conductor due to the external magnetic field. Due to the magnetic field we provide externally. Okay, let us go and explore it. So take a current carrying conductor here, a wire is there, and the direction of the current is upwards. So what is the direction of the magnetic field? That means what is the direction of the magnetic field line produced by this concentric circles, right? In this way. In this way, right? Now you place an external magnetic field here. This is north pole, this is south pole of the same magnet. Okay, what will be the magnetic field direction of this from north to south, right? It is in this direction, it is north to south. Now this current carrying conductor also has a magnetic field. This bar magnet also has a magnetic field. So this magnet experiences a force due to this magnetic field, right? Because it is under the influence of this current carrying conductor's magnetic field. Now in the same way, this current carrying conductor also experiences a similar force by this bar magnet, yes or no? This bar magnet will experience a force due to this current carrying conductor. In the same way, this current carrying conductor will also experience a force due to this bar magnet. If one we call as action, the second we call as reaction. If the force on the bar magnet we call as action, thus the force on current carrying conductor we call as reaction. Okay, and it will be in the opposite direction, that we know. So let us go and explore the direction of the force on this current carrying conductor. So first of all, let us see how the force will be experienced by this bar magnet at both sides. Okay, these two are connected. This is what we call as horseshoe magnet. Horseshoe magnet is nothing but a bar magnet which is bent so that the poles will be on the sidewards. Okay, so let us see now. Let us draw a magnetic field line through the bar magnet. Okay, now what will be the direction of the magnetic field? As you know, it will be current is going up. Take it, so it comes out of the board, go to the back end of the board and comes out. right? That will be the magnetic field direction. What is the magnetic field direction means? It is the force experienced by the north pole of a magnet. If you place a north pole here of any magnet, it will experience a direction in this direction. If you place a north pole here, it will experience a force in this direction. Okay? So you have a north pole here. Here what is the direction of the magnetic field line of this conductor? It is coming out, right? It is coming out. It comes out and goes in, and goes the back end of the board and comes out. So this north pole will experience a force due to this current carrying conductor right at you, right? Outside. Now we also see what is the force experienced by the south pole of the same magnet. See, the magnetic field lines is into the board now, but here it is the south pole. What the south pole does? It does exactly opposite to the north pole. Okay, if there is a north pole here, it will go, the direction of the force experienced by the north pole will go inside the board, right? As it is south pole, it will come outside the board because it is it behaves exactly opposite to north pole. Hence, this north pole is also experiencing the force outwards. This south pole is also experiencing the force outwards, right? So current carrying conductor producing a magnetic field is exerting a force on this horseshoe magnet outwards, right? You see that? Because this also, here also you have the force experience is outwards. Here, because of the south pole, it is exactly the opposite to the field line. The field direction is inside the board, the force will be outside. So this bar magnet is experiencing force outside due to this current carrying conductor. If that you call as action, now make this bar magnet steady and leave this conductor. So how the force on this conductor will behave? What will be the direction? If the bar magnet is moving out due to the force exerted by the current carrying conductor, what will be the force experienced by the current carrying conductor due to this horseshoe magnet? It will be right inwards, right? It is pushing this horseshoe magnet outwards. I am keeping this horseshoe magnet steady. Then I am leaving this. What happens? It will push it inwards. If this is outwards, that means coming outside the board. So if this is the action, what should be the reaction? If the coming out is action, reaction should be inside the board. So the force experienced by the current carrying conductor due to the horseshoe magnet will be inside the board and is exactly the same in magnitude but opposite in direction. That is what? The force on the conductor due to this external magnetic field, which is horseshoe magnet here. So this is how you see the force experienced by the current carrying conductor. Okay. So this is more mature way of thinking. Now to simplify this, our friend Fleming has invented a rule. What is called Fleming's left hand rule. It is just if you know the direction of external magnetic field and also know the direction of current in the current carrying conductor, you can easily identify the force experienced on the conductor. Okay, how is that? Let us go see. See, he's saying this is the B means B gives you, this is the magnetic field direction. Magnetic field direction. and this is the force, direction of force experienced by force of conductor of force on conductor. This is the direction of current inside the current, direction of current inside the conductor, inside the conductor. Anyway, the statement is given, but for your thinking I have just written it. So what he tells is, if forefinger shows the direction of magnetic field and this second finger shows the current direction inside the conductor, then this thumb will reveal the force on the conductor. Okay, let us see what he wrote. Hold out your left hand. That's why we call as Fleming's left hand rule. You can apply this rule only with your left hand. Okay, hold out your left hand with the forefinger, second finger and thumb perpendicular to each other. Perpendicular means 90 degrees. This is 90, this is 90 and this is 90. Okay, all the three fingers are perpendicular to each other. Now let us see what he is telling. If the forefinger represents the direction of the field, forefinger representing the direction of the field, and the second finger represents that of the current, so second finger is representing the current, so this, the thumb will reveal the direction of force on what? On the conductor. Okay, so this is how we formulated the rule. You can cross verify with the example we have discussed earlier, horseshoe magnet on the current carrying conductor, right? So you have a horseshoe magnet, in between you have a current carrying conductor. How the current carrying conductor will feel force inside, right, due to this. So let us imagine that again. Here we have a north pole, here you have a south pole. The magnetic field direction is giving this from north to south. Your forefinger gives the direction. What is the direction of the current inside the conductor from bottom to up, right? So this will give you the direction of the current. This gives you the direction of the magnetic field. Now unfold the thumb. See, it is inside. It is inside the board. We discussed the force experienced by the conductor due to the horseshoe magnet is inside the board, right? It verifies that. That's the beauty. Okay, so this is how we can calculate the direction of force on the conductor. Now let us see how it works practically. See, you have a setup here. Current is going in this direction. Use Fleming's left hand rule. Now magnet north pole, south pole, the field is in downward direction and it is experiencing a push towards the magnet. Cross verify it. Okay, let us suppose this magnetic field is downwards and current carrying conductor is having the direction inside the board. Okay, inside the board, because in this inside the board. Now it is going towards the magnet. See my thumb, it goes towards the magnet. If you see like this, it goes towards the magnet, right? The current is into the board, the magnetic field direction is from north to south, and this will be towards the magnet. That's what given here. You can see again. Let us observe keenly. Towards the magnet. You can rewind or you can see this video with minimum speed. Then you can see the slow motion of this. You can cross verify with your left hand rule. And how can you boil down this? Magnetic field is downwards. Direction of the current is into the board. Okay. It refers to the frame, this frame into the board. Now thus the force experienced by the conductor due to the magnet is from right to left. Right to left. Understood? You can again number of times you can cross verify this. You will get the same answer. And when you visualize anything, you close your eyes and visualize this is the direction of the current. this is the direction of the magnetic field, this should be the direction of the force experienced by the conductor, and open your eyes and see whether it matches your intuition or not. That is how you should what? See, you should learn the physics. You should always imagine in terms of pictures. When you imagine in terms of pictures, your idea of concept will get so your clarity of concept will be so much clear. Alright, it is followed by the great scientists called Einstein, Faraday, and these scientists used to see the mathematical equations and used to visualize those equations. And when they refine those visualizations, they will boil down to the concept, okay, this equation tells this, this tells this. So this is the way you should learn physics, in terms of pictures and imagination. And then you will have a beautiful doubts, and that also you will have the answers when you refine the question. Okay, hope you enjoyed this session. This is a very interesting session, I suppose. And before leaving this session, let us go and work out some problems. Okay, I have given you one question. So, did you hear about the electric motor? Something which is rotates, a motor which rotates. You pass electric current, it rotates, right? So we use this concept in the phenomenon of rotating. To rotate, we use this concept very cleverly. So don't study about the electric motor as of now. Just after this session, just think of how to rotate anything using Fleming's left hand rule. How to cleverly rotate anything using Fleming's left hand rule. You draw the diagram, do something, but you will have a clarity. You will try something, and when I explain you about the electric motor, you will understand it more clearly. That's what I mean. Okay, now let us see about the home assignment. When a current carrying conductor is placed next to a fixed bar magnet, will it experience a force in or opposite towards the direction of the magnetic field due to conductor? Justify your answer. So what here it is telling is, you have a magnet, you have current carrying conductor. Current carrying conductor will have a magnetic field lines around it. So if any magnetic field line is going through the magnet, what he's telling, will the bar magnet will experience the force in the direction of the magnetic field line or opposite to the direction of the magnetic field line? So that is the question. The second question is, an electron enters a magnetic field at right angles to it. The direction of force acting on the electron will be, that means we are asking what is the direction of the electron. The direction of force acting on the electron. Justify your answer. To give you a hint, current always travels opposite to the direction of the motion of electrons. So using this, you can easily apply Fleming's left hand rule and get the direction of the force experienced by the electron in this magnetic field. Hope you enjoyed this lecture, and we'll come back with even more interesting concept on application of Fleming's left hand rule, which is called electric motor. So thanks for listening. Sai Ram.